Okay, hello everyone. This video is picking up on where the last video left off. Last time we were talking about three-dimensional meshing. I believe we looked at a trimmer cell mesh. I have opened up that simulation and tweaked it a little bit to help get the cell count down a little bit. However, I wanted to talk about a little bit more about that, a little bit about a couple of meshing things, and a little bit about a couple of other things. The thing I want to start talking about is one that I already used a little bit of last time, but I want to clarify, or want to expand on that and go a little bit deeper into some of the other things. This is all about derived parts. There's a folder on the top level of the file tree. See it right here. These are not parts that have a static definition. This isn't saying this is a cylinder, this is a sphere with this position, this size, etc. Derived parts are parts that are derived from other parts. We have a couple of them already in this simulation. These are simply planes. Two-dimensional planes oriented in three-dimensional space. So they all have an origin, they all have a normal, and they're told that this part exists where that plane, defined by an origin and a normal, intersects with some part. In this case, they've all been told that they exist where these planes intersect with the simulation domain. Where this plane, numerically, intersects with what we are simulating, the air around this airfoil. You can see I clicked on this part and it's highlighted a kind of wackily oriented plane, but it only exists inside of this block that is our air. This is just one plane, but there's modes where you can have multiples. You can have, let's say, two sections, and you can have them 10 centimeters apart. I don't know if it's updated yet, but it should. Oh, yep, there we go. So we can now see that this is actually, because I told it 4 planes 1/10 of a meter apart, well, it has 4 planes 1/10 of a meter apart. There were 2 planes here before, they were just so close we couldn't see them. So these are plane sections. There's actually 2 more in here as well. There's one right here that I'm using to visualize the mesh. There's another one right here that I'm using to visualize the mesh. These cut through their planar sections, cross sections, of, in this case, the air. You could tell it to make a cross section of whatever the heck you want. Let's say, for example, instead of the simulation domain, I wanted this to be a section of my wing. Doesn't actually seem to have done that very well, but let's see here. There we go. If I select just the surface of the wing, it said, hey, this plane intersects with this surface along this faint purple line here. It's very hard to see because it's literally a line in two-dimensional, or in three-dimensional space. An infinitely thin line. It's kind of hard to see. But as far as selecting stuff goes, you'll notice there's actually a couple different selection boxes here. This is worth explaining. So, a lot of parts, specifically anything that has a physical volume to it, will actually have multiple selection boxes. I really wish I could zoom in on this, but I really can't all that easy. So, it has this little like triangle of boxes here. It has a big box to the left, and it has two smaller boxes to the right. These all have specific meanings. What the big box means is that it is just selecting the volume that is the simulation domain. Not any of the surfaces, the volume. So if I click OK here, this plane will intersect with the volume of our simulation domain and highlight where it intersects with the volume. Not worried about the sides of the box, it's just worried about the volume of that air. You can select everything where it will highlight not just the volume, but also the sides. But that's kind of hard to see because it's also showing the volume. So let's do this another way, where we are going to select just the sides and not the volume. Well, look at that. It highlighted the surface of our airfoil, it highlighted the edges of our box, but not this entire section in the middle. It's highlighting where this plane intersects with the surfaces of this part. It's highlighting where this plane intersects with the back, the bottom, the inlet, out of plane side, the top, the airfoil trailing edge, the airfoil surface, the airfoil wingtip, etc. It's highlighting where it intersects with the surfaces, not the volume. In this case, we're just going to leave it as selecting the volume because that's kind of really what we cared about. This is one type of plane section, or one type of derived part, excuse me. There are others. Take a look at a few of them. Let's see here. Cell surface. Let's look at, let's see here, the wingtip and see what this looks like. Well, this part is highlighting all the cell surfaces associated with the wingtip. I won't do anything to show it, but hypothetically, if we change the wingtip, this part would change. I'm just going to delete that. We have isosurfaces. Now, I don't think this has a solution on it, so this isn't going to be very useful yet. But an isosurface is a surface of constant value. It is where a surface has, or it is a three-dimensional surface, or in 2 dimensions it could be a curve, that has a constant value everywhere. So, there we go. So I asked it to show me a surface in the simulation domain where pressure is a constant -5 pascals. 5 pascals below our reference value. And it's shown us. So there is this surface, and everywhere on this surface, which is mostly where we expect, right? We see that inside of this surface, the pressure is going to be above -5 pascal. Or sorry, it starts out at 0. So as it crosses this surface, it is going to be below -5 pascals. As it exits the surface, it's going to be crossing through -5 pascals and increasing again. So the inside of this surface is below -5. The outside of the surface is above -5. We get a very large region of lower pressure above the airfoil, and a small region of lower pressure, but it's definitely not as low as the pressure on top. And at the leading edge of the airfoil, where we expect a stagnation point and relatively high pressure, we see that there's kind of a slot in this surface. Exactly what we would expect to see. And it is a little bit lumpy just because the mesh is relatively coarse, actually. And it only knows, which cells have a pressure. Each cell has a constant value for pressure. We're seeing some three-dimensional artifacting of what does this mesh look like in 3 dimensions. You could look at temperature, you could look at velocity, you could look at a great many things. You can select whatever the heck you want. It doesn't need to be pressure. It could be absolute pressure. You could look at viscosity, although that really wouldn't change. You could look at density, even though that wouldn't change very much for this. Heat transfer coefficient, any of these, Mach number, you name it, you can look at it. Any of these field functions, any of these scalar field. That's an isosurface. Again, it's a surface where everywhere on the surface, it's a constant value. What's a constant value? Your choice. The important thing is it does have to be a scalar quantity. The next one is probes. These are quite useful, and these are ways of taking data at specific points. You might say, hey, I want to measure something at a point. Well, you put down a point probe. You define its coordinates, x, y, z, and you define what domain it is a part of. In this case, I want to measure, let's say, well, actually, it doesn't matter what I want to measure. The point is where I want to measure it. So if I wanted to measure pressure there, let's say, we create a point. See, it's highlighted. There's a point floating out in space. But it doesn't do anything by itself. Right? If we want to measure something, we need to go create a report and say, hey, I want to know, because this is a point, we can't do anything fancy with it. But let's say I want to know what is the pressure at that point. Because it's a simple point, the maximum, literally, it's a point in 3-dimensional space. It has no volume, no length, no area. It is a point. So if we look at pressure, and we ask for the maximum pressure. Oh, wait, sorry. That's a co-located field. That's not what I wanted. Sorry. If we look at pressure on that derived part, we can run this report, and it'll tell us that the pressure there is pretty gosh darn close to 0. It's 0.006 pascals. Now, if we wanted to know the pressure much closer to the leading edge, we can move this part. I said, let me walk through that again real quick because I did that a little bit fast. If we want to move it, if we want to move really any of these, we can say edit part in current scene. If you have a geometry scene open, you can edit it with sort of a GUI in the scene. So I'm going to try and move this relatively close to the airfoil. Or wing more properly, because this exists in 3-dimensional space. I'm trying to measure pressure just underneath this wing, kind of near the wingtip. I changed where this point is. I hit apply, it'll update where the point is, and we can see that it's highlighted now just underneath our wing. We run this maximum report again. We see that, oh hey, pressure is negative 2.51 pascals instead. Edit this part in the current scene again. Move it up. Apply. Run this report again. Ah, now it's negative 25 pascals. Exactly what we'd expect. We have a lower pressure on top of the wing than underneath. We can do other things with probes. There are line probes where you have a series of things between 2 points. So if we wanted to make a whole bunch of probes on a line connecting those 2 points, we absolutely can do that. In this case, this between these 2 points, defined by XYZ coordinates, it will place 20 probes. Now, this one, if we ask for the maximum, it's going to give us just one value. It's going to give us what is the maximum value along that line, which is a grand total of 0.05 pascals. Not very big. We can click on it and see that it put 20 points on a line that connects those 2 points through this domain. Actually, I think this might be 18 because I think technically the first one and the last one cut off. 3, 4, 5, 6, 7, 8, 9. Nope, it's actually 20. It's actually 20 points between those 2 points. We can also do a grid, which is a 3-dimensional thing, right? And we have a center, we have a normal, and we have where it intersects. It has corners, which are calculated, and it has an X and Y resolution. I'm going to turn this resolution down a little bit. And hit no displayer so it doesn't show up, but click create. And we can see that it's put a grid of points everywhere in that domain. Look at that. We can look for the maximum on that. Let's see here. What is the maximum on this grid? Okay. It's ever so slightly less than the maximum on our line was, 0.048 pascals. Or we could ask for the maximum across multiple things. We don't just have to select one. We can select more than one. Now, since we selected both the line probe and the presentation grid, it's probably going to tell us our maximum is this 0.051. Yep, 0.051. It found the maximum for our grid was 0.048, and our maximum for our line was 0.051. So it told us that, hey, the maximum is 0.051. Probe, also arbitrary. This one is a little bit weird, but you can put it on surfaces. You can do a couple of interesting things with it. If you really think that's going to be useful, you can refer to some of the help documentation. But this put a bunch of points on the surface of the airfoil. Oh, hey, that could be very useful. Look at that. You could plot, or you could potentially do measurements and plot pressure distribution over an airfoil or over a section of the wing. That could be very nice. It really didn't change anything, did it? Let's see here. Let's try and deselect our faces and see what this. I think that actually is highlighting the wingtip incidentally already, because let's just take a look here and click on our wingtip boundary. Oh, hey, yeah, that's already highlighting our wingtip. So what it was doing, I'm pretty sure, is highlighting edges or highlighting points on the edge of that surface. But that one's a little bit more advanced, but you can mess around with it. The next one is sections. We already talked a little bit about a section plane, but you can also have cylindrical sections, spherical sections. You could alternatively have a plane that is constrained by something. Constrained by, in this case, this works the exact same as a section plane. One important difference. You can make it so that plane only exists between a curve of your choice. So this section plane, this arbitrary plane, will only exist inside of that curve that I just clicked out. I clicked out a random curve that looked vaguely like that. It highlighted cells that exist with their center, I believe it's their center point, inside of that curve. It didn't highlight anything outside of that curve. It only highlighted what was inside of that. It is a constrained plane that is constrained to a curve of your choice. Section, arbitrary. You can make a section that is constrained to, let's say, this. I'm not exactly sure what this is going to do, truth be told. But it looks like it made a section that is constrained just to where the simulation domain is touching that wingtip. So it effectively highlighted the wingtip. Makes sense. Streamlines. This one could be important. Actually, this one is important. Streamlines have a very simple definition. Everywhere along a streamline, the flow is tangential to the streamline. The streamline shows you what direction the flow is going, and it can show you a property of the flow. Actually, I should back up. It shows you the direction of a vector quantity in the flow. Doesn't have to be velocity. It's usually velocity. But hypothetically, you could use any of these vector quantities that it lets you highlight. Vorticity might be another one you use. But usually you use velocity for streamlines. So you can create a couple different types of streamlines. They have a couple different modes here. You tell it what part do you want the streamline to be a part of. In this case, we want a streamline through our simulation domain because this is the air that we care about. You can tell it to snap to a part. Could be a derived part. Could be some part of our simulation domain. Doesn't really matter. Snap to part, this will make more sense in a second here. And then you tell it, where do you want to seed the streamline? Well, what does this mean? Again, streamlines are paths that are tangential to some vector quantity in the flow. But where do you start those lines? Well, depending on where you start the line, you'll get a different set of streamlines. You start the line in one place, it'll effectively follow the flow from that location. So we can select where to start the flow as a point. We can select a whole line. Or we can tell it to start on a surface. So we can tell it, hey, I just want streamlines that extend from our inlet. And I want this to be a 5x5 grid of streamlines. Or, hey, I want a single point. Or I want a bunch of streamlines that all start within some radius. Let's go 1/4 meter. Okay. 1/4 meter radius from this point, I want to generate 5 streamlines. Now you can click the display tool button to make it show up. And you can move it around the scene to put it where you want. You can also say snap to part. Notice it got snapped to our airfoil. That's what I had selected. That could be a handy way to move it kind of where you want. So we can put our point there and go ahead and click create. And we get some streamlines. So let's take a look. Hey, look at that. We have streamlines. Got some flow going over our airfoil. We got some flow going under our airfoil. It's great. Let me look at this from the other side. It might be slightly more obvious what's going on. We have a little bit of span-wise flow. Not very much, but a little bit. Notice how the flow is kind of curving a little bit here. And we can change the number of streamlines. Let's say we want 15 points. Takes a second to recompute. We have 15 streamlines now. Let's say we want this to occur in a much larger radius. Oh, click up the radius. It generates a much larger radius of streamlines. Perfect. Now note, this isn't extraordinarily accurate right now. This simulation is not converged, but this serves to demonstrate some of the things. We can also, as I said, instead of seeding a point, we can seed a line. Let's edit this part again. We display our tool, we can see that we have a line. Let me snap this line to our wing really fast. So our wing face. We have a couple of points that we can move around and draw with. So let's say something like that. I'm going to put 40 streamlines along this line. Don't go totally bonkers with the number. Notice that took a moment to calculate. But hey, look at that. We've got streamlines, 40 of them. Nicely trace out the flow around this airfoil. Streamlines are very useful. Not just to show you the path that a thing takes, but they can also show you values along that path. Let me show you what I mean. Let's create a new geometry scene. We have our box. Let me hide some of the outside walls here. And I'm going to go down here, this geometry scene 2 that we just created. And I'm going to create a new displayer. Specifically, a streamline displayer. So right click, new displayer, streamline. Okay, well, first off, we have a new streamline displayer. We can see it right here. We have outline 1, which we really don't need. We have our surface 1, which is showing us the surface of our wing and our box that we haven't hidden. And we have streamline 1. Let's tell streamline 1, this displayer, to show us our streamline. Hey, look at that. And they're not highlighted. They're just there. They're showing us our streamlines. We could have it show us stream tubes. We can show just lines. We can show ribbons, which also kind of shows you the rotation of the flow. There are various uses. I tend to be partial to stream tubes, and we can make them a little bit thicker. Let's say instead of 0.002, let's do 0.008. We have little tubes that are following the flow. Now let's get fancy. We don't just need to see the path. We can look at properties. Let's look at what does pressure look like. along these streamlines. Ah, look at that. Again, not fully converged yet, so take it with a grain of salt. But we can see how pressure changes. Top and bottom, everywhere along these streamlines. All the way out to the back of the domain, or until the streamline ends, whichever comes first. Streamlines do not have to go forever. If we go back up to the streamline really quick, we can see that there's some options here for integration. You want to follow the flow forwards. You want to follow the flow backwards. Or do you want to follow the flow in both directions? How far do you want the flow to propagate? Maybe you only want it to propagate like 10 meters. Look, it stops 10 meters downstream. Maybe you only want it to go 5 meters. Hey, look, it stops 5 meters in both directions. Note that the back edge isn't straight because the flow took different length paths to get here. How long do you want to actually integrate for? Maybe you want to make sure it doesn't integrate for super long. You can turn up or down the number of steps. Which, if it runs out of maximum propagation distance, if it runs out of maximum steps, it'll stop calculating a given stream. Streamlines can be very, very powerful. Constrained streamlines work largely the same way, with some additional restrictions. So we can use a streamline in our simulation domain. We're going to do a line seed. We're going to display our tool here. And we're going to put it right there like before. Move this around so it's not quite as three-dimensional. But we're going to give it a little bit of three-dimensionality here. Vector fields. We're going to go with velocity. We're going to add it to our existing streamline displayer. And create. Let's see what this looks like. Oh, it doesn't look like it did much of anything now, did it? Let's try Dicity. See what this looks like. Okay, well, not 100% sure what this one does in actuality, so let's check the help documentation. What does that say about a streamline? Defining a streamline, where's a constrained stream? Seed, source seed. Let's see here. Well, that's a little bit annoying. It doesn't actually call it out. No matter. What else we got? U-part, vortex core, separation attachment point. Threshold. The threshold's an important one. Because we can use it to visualize stuff. We can also use it for debugging. So, I'm going to describe some of the things here. A threshold part says, okay, hey, basically, give me any cells in a part. So give me any cells in some combination of input parts. in this case our simulation domain, that have a value that is above, below, or within some limits you specify. So let's look at good old pressure. Actually, that might be our constraint. That might be our constraint streamlines right there. All those little dots right there. But no matter. Let's say I want everything that's between... No. Everything that's outside -5 to 5 pascals. If it's between those values, it won't show us. Create, and let's click on, where's our threshold? Take a second. Aha! Every cell it just highlighted is between -5 and 5 pascals. And just so we can see it without me highlighting it, I'm going to add that to our geometry scene. Ah, look at that. We got cells. Which also helps us visualize what a polyhedral mesh looks like in 3 dimensions. Every cell it just showed us is either below -5 or above negative or above positive 5 pascals. We could also change that value. We can say, hey, no, I don't want anything outside of this. I want only what is below our minimum. Boom. I only want what's above our maximum. So we have a couple of pockets of high pressure that it highlights. I'm not going to select between, because between those values is 0. Well, guess what? Pretty much anything that's not near the airfoil is 0. Actually, you know what? Hell, let's just go ahead. Between. I'm going to highlight pretty much everything except for a chunk in the middle, right? Works pretty well. This can be very, very, very powerful. It can be especially powerful for debugging. What happens if, like, you're doing a simulation and your maximum velocity is, for a subsonic airfoil simulation, your maximum velocity is 500 meters per second? Well, something's probably wrong, because there's no way in hell velocity around a subsonic airfoil should be getting that high. Well, use the threshold part. You can highlight any area where your velocity is above, let's say, 200 miles per hour. That would show you the spot where your velocity is above 200 miles an hour. That would probably show you where you might have a problem physically, which can be important, because you can look at parts of the mesh. You can use section planes. You can use other types of planes. You can look at surface meshes. But it's really hard to know what every corner of the mesh looks like. It's almost impossible to know what every corner of the mesh looks like in detail. But if there is an issue, sometimes there will be, you can use threshold parts to find where that issue is. Or just highlight regions where there's high pressure, or velocity, or temperature. Take your pick of quantities. Pressure and velocity are going to show up because I'm going to tend to use airfoils and other aerodynamic things as examples. But you can use any scalar field you want. Any scalar field. Look at the, let's see here. The wall y plus distance. Let's look at anything outside of 1. Or anything above 1. Oh, well, that one's not going to show us anything. You figure out why, or if you want to think about why, go ahead and pause it here and think about it for a minute. Good on you. You'll recall that there's 2 different types of selections, though. Right now, we're only looking at the volume in our simulation domain. We're not looking at surfaces. Let's look at surfaces, too. And let's look at... Let's see, is this actually going to show us anything? Okay, now I'm a little bit perplexed why isn't showing us anything at all. -1 space 1. To 0.05, 0.05 to 2. Outside? Green? Curiouser and curiouser. That one has me a little bit confused. Let's look at velocity and just see what the velocity magnitude looks like. Well, velocity in most places is pretty high. Much higher than a couple meters per second. But the no-slip condition is the thing. So, near the surface of the airfoil, all these cells have a very low velocity. Let's look at above max, and it's going to highlight the entire field. Look at below min and give it like 10 meters per second. This should be a bubble of flow of the boundary layer. Look at 40 meters per second. Well, I think I overcooked that one a little bit. 25? $18. There we go. We have a couple regions of high velocity flow as the flow moves above the surface of the airfoil. There's a tiny gap in here because there's a boundary layer in there. But it highlighted all these high velocity cells. The cell, or the velocity in these cells, is above 18 meters per second. What other derived parts do we have? There's a couple others. These are fancier. We're not going to talk about them too much. Threshold is a very useful one. For another reason. You may recall, when running these things, you get a plot that looks like this. The residuals. You can see this one hasn't run out very far. If you're having a problem and your simulation is crashing, might be due to a bad mesh, might be due to a bad boundary condition, could be any number of things. But you don't know why. It should be working. Why isn't it? Happens all the time. Because again, you're never going to be able to get everything exactly just so for any realistically complex simulation. You're going to be able to get it close, but you might have problems in corners and not know about it. And it's crashing. You need to fix that. Obviously, you need your simulation running. But we can find out where there's a problem. So, debugging. How do we find out where the problem is so we can fix it? Well, one of my favored ways, if you do reach the point where your simulation isn't working, you need to debug it, is to use a combination of threshold parts and a couple other options, and also some minimum and maximum reports and things like that. So, let's talk about the reports for a second here. You can create a report for minimum values and maximum values. Let's make one for maximum right here. We need to turn on a setting here. So before I get into that too much, let me back up a step. Where do these residuals come from? I think I may have discussed this before, but if I didn't, I'm going to discuss it again. So, where do these residuals come from? When it's doing this math, it's a crap ton of linear algebra and series expansions and a whole bunch of matrix math. The problem is, you can't calculate these things to infinite precision. You'd be there forever, literally. You need to have some amount of finite precision. You need to stop your calculation at some point. And what the residuals are basically what is left over after you stop your calculation. It knows how much is left over in every cell after it stops its calculation, and it can add that up, and it can normalize it. By normalize, I mean it takes the value for the first couple of iterations, treats that as a value of 1, and then if it goes down, it's a value of less than 1 for the future iterations. If it goes up, it's a value of greater than 1 for the result. After it's done with that, it throws out the value for every cell. It doesn't need it. It doesn't need to remember the residual value for every cell. It already summed them up. It already gave you an overall value. Got rid of what it used to do that. Because that's memory it can use for something else. That's all well and good. Except if you want to know exactly where the residuals are high. If you want to know where the residuals happen to be higher, then you need to know what cells have what residual value. Well, smart people that they know that this is a solution to a problem. So we can turn that on. If we look under solvers, this has a whole bunch of settings that govern some of the low-level math that the solver does. I won't go through all of it, but I will point out a couple of useful settings. Namely, we click on segregated flow, you'll see this button, temporary storage retained. We can ask it to hang on to those residuals. What would normally only be temporarily stored will be retained. And then there's one of these for each of the primary solvers. So for flow, which is continuity and momentum, for energy, which is energy, and for turbulence, which is its own separate thing, can all retain its own temporary storage. I'm going to have this iterate once, because right now, currently, it's already thrown out those values. For iteration 13, iteration we're on, it already calculated the residuals, it added them together, it normalized them, and it threw out the per cell values. If we want per cell values, we need to make it calculate them again. It means running one iteration. So, I'm telling it to run one iteration, and we'll give it a minute. Right, okay. All of these residuals jumped up. Why? Well, if you want to think about that for a second, pause the video. If you just want the answer, here it is. It's because we changed the mesh. At iteration 13, it was a trimmer mesh. I remeshed and made it polyhedral, so all the cells change not just how big they are, they change shape and everything. Because all these values changed quite suddenly, the residuals jumped quite a lot. Because everything changed quite rapidly. So what's left over in those equations when it's calculating them got quite large. If we kept on iterating, theoretically these should come down. But the important thing is, now we have those values. We have values for residuals on a per cell level. We can ask this maximum, hey, residual, what is my turbulent kinetic energy residual? Where is this calculation leaving the most on the table? Or sorry, what is the maximum value of the residual for turbulent kinetic energy? What is the most that it is leaving on the table for any one of these cells when it's doing this calculation? That's going to be useful in and of itself. So we're going to ask it, where is the cell in our simulation domain that has the highest turbulent kinetic energy residual? Or what cell, or what is the value of the highest turbulent kinetic energy? We can also ask it where. When you have a maximum or a minimum, by definition, there can only ever be one. Which means, by definition, you are only ever talking about one cell. So, because you're only ever talking about one cell, you can do this interesting thing. You can have it find the maximum or minimum, and then you can ask it other things about that cell. Because you can only ever logically be referring to one cell with this inquiry. That is what these co-located field functions are. It says, hey, I want to know what are these other things where this maximum occurs. You could ask it, what is so many different things? The list is, 301 entries long. So many different possibilities. The one that is most useful for debugging is either a quantity of interest, like you can ask for maximum pressure or something, but also, perhaps the most useful, position. Not position magnitude. You can ask for its coordinates in XYZ position in a coordinate system. This will tell you not just what is the maximum, but where is the maximum. So, this suggests that if we're having a problem with turbulent kinetic energy residuals, it's probably occurring at negative 0.43 by 7.458 by 9.499, rounding off a little. That's probably where the problem is if there is one. Not that there necessarily is a problem, but if there is, this could help you find it. Sometimes it's not that simple, though. Theoretically, you could have several different problems in several different places where one of them is slightly worse than the other, so shows up first. You could spend all day playing whack-a-mole, dealing with all the maximums, and finding a new one that's still a problem. That can happen. Been there, done that. But we can also check out a little bit about where might there be other problems. How do we do that? We look for an area of the flow where our turbulent kinetic energy residual is close to our maximum. Most of the flow isn't going to be anywhere near that, but in some places it's going to be close to that. So, we now know what the maximum is. We can ask our threshold part. We can ask our threshold part. Where did our derived parts go? Derived parts. There we are. We can ask our threshold. Okay. Instead of talking about velocity, pressure, any of these other things, let's talk about our turbulent kinetic energy residual. Okay. Let's open up our geometry scene. And let's put this value at something just below our maximum. Let's go with 0.15. This can involve a little bit of binary search because you don't necessarily know exactly how much distribution it is. Well, there's a pocket of flow up here that really doesn't like where it is. It's actually pretty far away from the airfoil. So these cells have a residual above that value. Might be an issue or might not. It's impossible to tell right now because the simulation isn't necessarily unstable. It's only run for 14 iterations. But we can look for other pockets that are, in this case, all of these are greater than 0.1. 0.05. More pockets. You get the idea. As more and more of these pop up, we're going to get more and more cells highlighted. 0.1, etc. Let's look at X momentum instead. Well, if there is a problem with the simulation, this would pretty strongly imply it's because our cells are getting a little bit big towards the outside. Again, not that there necessarily is a problem with this simulation, just that we could use these tools, these threshold parts, and these residuals to find out where that problem is likely located. Debugging. Okay. That's very useful if your simulation keeps on blowing up. It just keeps on blowing up. Well, I don't particularly have a good, reliable way to make it blow up super reliably that I know of. I generally try and avoid that. But if you do blow up, you'll get a nasty gram in the middle there that says like floating point exception in KE or KO dot turbulent or segregated dot flow solver or something like that. What that means is numerically, mathematically, something blew up. Something got so large that a floating point or a double floating point value is no longer large enough to contain it. That's what that means. So if you ever get one of those errors, that implies that something's probably wrong with your mesh. Or if you, again, you get a value that's so far out of the realm of plausibility that's just certifiably insane that it would be a physical quantity. So it has to be a computational issue. Again, something like, hey, our flow velocity came in at 50 meters per second, and it's making it to 1,000 meters per second somewhere. That could very well be a sign, or that is a sign, that you've got a problem in the mesh somewhere. Because you know that just shouldn't happen under pretty much any circumstances. Barring some potential very unique applications with a like very high pressure convergent divergent nozzle, maybe. Maybe your flow comes in at only a couple meters per second, but leaves at going like Mach 3. That's a thing. It's basically a rocket engine, right? But you would have an idea if that was plausible or not for any given scenario. Okay. The only other thing I really wanted to discuss is involving volume controls. We've discussed surface controls. We've used surface controls, but that's not all we can do. Especially in 3 dimensions, surface controls sometimes don't cut it for refining the mesh. Maybe we want to refine this area like right near the leading edge of this wing. That's great, except how do we define it? This is a curved surface. This is all one surface. What if we just want this area in the front to be smaller? Smaller to a specific amount, for example. We don't have a surface to define that, but we can make a volume that encompasses that area. Let's go ahead and make a cylinder here. New shape part, cylinder. And that's definitely a big cylinder, so let's go ahead and knock this radius down to something like 5 centimeters. Couple inches, couple inch radius. Pretty small cylinder. Zoom in on this. Okay, it's centered at the leading edge of the wing because the wing is centered at 0, 0. So this happens to extend in the z direction. It goes from 0, 0, 0 point out to 0, 0, 2.5, I think. I forget exactly how far this wing extends. 1.75, maybe? 1.6, let's say. Okay. So this cylinder should extend from where the wing starts to slightly past where the wing ends. Oh, I just moved it. 0, 0, 0. If I don't want to move any of these, I can hit lock, and that makes sure that it won't move. I am, however, going to bring it back to negative 0.1. So it's extending 0.1 meters on either side of our cute little wing here. Although I'm pretty sure that's a plane, so that it doesn't matter on this side. But on this side, it extends a little bit past the airfoil. We're going to create the cylinder. we have a cylinder. Let's highlight this cylinder. There we go. We have our cylinder. Hide some other parts. We have our airfoil, or our wing, excuse me. We have our cylinder. So how do we use this to refine those cells near the front? Well, if we want to refine our cells, that means using a mesh operation, right? So let's do operations, automated mesh, and we can make a new custom control. We can make a volumetric control. Okay. Well, let's say we want to refine any volume inside of that cylinder we just made. Any cells inside of that cylinder will be affected by this volume control. What do we want to do? Probably customize the polyhedral mesh. Let's make it something painfully obvious. 50% of base size. Let's take a look at our mesh scene just to make sure. The answer is 50% might not actually be enough. Let's do a little bit of measuring and find out. So these cells are about 3.5 millimeters ish. So I'm gonna make this smaller inside of that cylinder. Everywhere inside of this cylinder, the maximum cell size should be no greater than 1.875 millimeters. And we're going to execute. We're going to execute this and wait. But while we're waiting, let me mention a couple things here. So the first thing is that it doesn't necessarily need to redo the surface mesh, although it might be anyway. When you change something about the volume mesh, and only the volume mesh, it knows what it needs to update or not. You don't change anything about the surface remesher, it is not going to rerun the surface remesher. It'll only rerun the stuff it needs. The second point is that with volume controls, you gotta be really freaking careful. Because with a surface control, you're affecting a surface, right? It exists in 3 dimensions, but it's a surface, right? If you have the cell size on a surface, you're only increasing the number of cells by approximately a factor of 4. Right? Because if you take a line and you break it into 2 pieces, well, you've increased the number of lines by 2. You take a square piece of paper and you break it so no length is longer than half of the edge of the piece of paper. You're going to break that piece of paper into 4 squares. What was once 1 became 4. That will pretty much be a statistical average that will hold. The problem with volume controls is if you take a cube and you break it into edge lengths, if you break the edge length down by a factor of 2, you're not left with 2 cubes. You're not left with 4 cubes. You're left with 8 cubes. So if you're not careful with volumetric controls, your cell size can absolutely explode on you very easily. So if you're going to use a volumetric control, make it as small as you possibly can while still encapsulating the area you want. And whatever you think you need, probably start with double what you think you need, just to make sure. Because you will be rudely surprised. Use a volumetric control, you go back to look at it, and 95% of your cells are in that little box you just made. Or that little cylinder you just made. That will happen. You will be sad that you just wasted a half hour to an hour letting it mesh when the mesh is useless because you'll never be able to run it. Because volumetric controls scale exponentially to the 3rd power. And exponents are very non-intuitive and will get you in trouble very quickly. That's part of mesh scaling in general, is this weird interpolation between the fact that you have square factor growing for surfaces, you have cube factor growing for volumes, and how they interact in weird ways results in definitely not true exponential growth, in the sense of it's not a cubic growth, it's not a square growth. It'll be somewhere in between, depending on how they interact and how all these controls interact. For example, if none of the cells are making it to the maximum cell size, maybe doubling or having the cell size actually doesn't hurt all that much. Because, yeah, sure, the cells really close to surfaces get smaller, but the cells further away are going to get a lot bigger. So it'll increase your cell count, don't get me wrong, but it might not do it by as much as you expect. Or it might be the opposite, where, like, hey, I made the maximum cell size, I reduced it by a factor of 2. Well, guess what? If most of your cells were their maximum size, you just increase your cell count by a factor of 8 almost. That could be bad. But anyways, this thing just finished remeshing, and we can see that in a cylindrical shape near the leading edge, show by highlighting our cylinder. Like that. It's a lot smaller. Everywhere in that region is a lot smaller. So we're down to about 4 million and change cells. Not claiming that this is a good mesh necessarily, but that's a way that a volumetric control could work. We could do the exact same thing behind this wing. We could do the exact same thing in a cylinder or a cone or a block near the wingtip. Or you could create some weird geometry in an external program, import it, and say everything in this weird oblong ellipsoid shape should be refined. Doesn't matter. If you can point the simulation to a three-dimensional, a part with three-dimensional volume, you can apply a volumetric control to that. So, these things are, we started a little bit with, I believe, the derived parts. We can see what a polyhedral mesh looks like. We talked about setting up some probes so you can measure things. Point probes, line probes, arbitrary probes, presentation planes, section or presentation grids, for measuring points on a grid. Plane sections, we also have cylindrical sections, constrained plane sections, spherical sections. You could cut up your domain into a bazillion different ways. Streamlines, those will come back. Believe me, they'll come back. Thresholds, very useful for debugging and visualizing regions of higher or lower values. ISO surfaces, also fun to deal with. Can be very useful depending what you're doing. We talked a little bit about how to debug, specifically using thresholds and reports to find where there might be a problem, or that you know there's a problem, how to find it. It won't necessarily tell you that there's a problem, although they could, depending how alert you were. We talked a little bit about volumetric refinements and how you can refine regions of the flow in three-dimensional space. Not just surfaces. Also very powerful, though potentially dangerous. So, that's it for today's knowledge dump. As usual, if you have questions, you know how to get a hold of me to ask them. If I use this for future semesters, this might not necessarily be the case, but at least for the immediate future, if you have questions, drop into the actual workshop hours that are the class and ask them. I will happily walk people through the detailed implementation of any of these steps beyond the scope of this video. If you're having trouble following, let me know. Happy to explain. Send me a Canvas message if part of this was unclear. Parts of it probably were unclear. I've been using this software for a long time now. Some things that are going to be second nature to me, I'm just not going to think about telling you. It's not going to occur to me. If you're completely lost about part of this, maybe watch the video back a little bit slower, see if you can follow it. But if you still can't, let me know with a Canvas message. Maybe I need to clarify. If it's that bad for you, it's probably that bad for somebody else. I can go back and make an announcement, make a short supplementary video, do something to help clear up the misunderstanding. But other than that, I will wrap this one up and post it, and I will speak to you during class.